The universe is full of incredible mysteries that challenge everything we think we know about reality. As we look deeper into space and study the smallest particles, we uncover strange and surprising ideas about how our universe works and what might happen to it in the distant future. From the idea of time flowing backward to the possibility of hidden dimensions colliding, these theories push the boundaries of science and stretch our imagination. Each of these mysteries raises questions that have no simple answers, and exploring them helps us see the universe in new and mind-bending ways. Join me as we explore the mysteries of the universe. The Sachs-Wolfe effect. The Sachs-Wolfe effect reveals the cosmos's faintest signals, mapping invisible forces and the oldest moments in time. Imagine looking at a photo taken over 13 billion years ago, yet instead of a picture, it's the subtle temperature differences in cosmic microwave background, CMB radiation. The Sachs-Wolfe effect, named after scientists Rainer Sachs and Arthur Wolfe, captures these tiny variations in temperature and light caused by gravity. It acts as a fingerprint, marking the influence of gravity on light as it journeys across vast stretches of space. These faint shifts in CMB temperature provide critical clues to understanding cosmic inflation, the age-old stretch of time when the universe rapidly expanded. One key aspect of the Sachs-Wolfe effect is how it demonstrates gravitational redshift, the way light loses energy as it leaves a gravitational field. This effect occurs when light from the early universe passes through massive clusters of matter. As light fights against the gravitational pull, it loses energy and changes wavelength slightly, revealing where powerful gravitational forces once lay. This temperature map, essentially a subtle gravitational map, gives scientists a peek at the large-scale cosmic structures that influenced galaxy formation long ago. Without the Sachs-Wolfe effect, we might not know how certain regions of the cosmos, rich in matter and energy, shaped the universe's appearance today. The Sachs-Wolfe effect also shows us how faint temperature differences across space reveal clues about dark energy, a mysterious force causing the universe to expand faster over time. The effect varies depending on the strength of gravitational pulls across the universe. When photons, particles of light, from the CMB cross through clusters of galaxies, they gain a slight boost, then lose that boost as they exit the gravitational field. If dark energy weren't pushing the universe apart, this boost loss would balance out, and temperature differences would be predictable. However, scientists observe small inconsistencies in these temperature maps. These inconsistencies suggest that dark energy is changing how photons interact with gravity, indirectly showing the presence of dark energy without ever directly observing it. Beyond revealing dark energy, the Sachs-Wolfe effect holds the earliest imprints left by the universe's first moments of inflation. During inflation, quantum fluctuations, small random shifts in energy, were frozen into place as space expands faster than light. These fluctuations created density differences, which became the blueprint for galaxy clusters. The Sachs-Wolfe effect picks up on these early density differences, allowing scientists to trace back the growth of the cosmos from the smallest quantum shifts to massive structures that hold thousands of galaxies. These tiny CMB temperature differences also serve as a measure of the universe's flatness, which is the shape or geometry of the universe. Observing a flat universe means that, on the grandest scale, space behaves like a flat plane with little curvature. Sachs-Wolfe measurements support this idea by confirming that small temperature fluctuations fit well with a flat universe model. Any significant curvature would cause distinct changes in the temperature readings across different points, but scientists observe a relatively consistent pattern, reinforcing a flat geometry. This insight affects everything from how gravity behaves on a cosmic scale to how scientists predict the universe's future shape and expansion. An interesting byproduct of the Sachs-Wolfe effect is the so-called integrated Sachs-Wolfe effect. The gravitational fields between galaxies are altered when the expansion of the universe is caused by dark energy. Depending on the strength of the dark energy field, photons passing through these fields experience small energy gains or losses. These changes manifest as extra temperature variations in the cosmic microwave background, CMB. Scientists can indirectly see the effects of dark energy on the cosmos through the study of the integrated Sachs-Wolfe effect, rather than directly observing dark energy itself. Experiencing the sensation of wind without really seeing it is the closest analogy. Another clue about cosmic history is that the Sachs-Wolfe effect reveals traces of hidden, missing baryons. These are particles like protons and neutrons that should be out there, making up ordinary matter, but have eluded direct detection. Studying CMB temperature changes allows scientists to infer where these baryons might be hiding. The fluctuations left in the Sachs-Wolfe signal hint at patches of baryons floating in intergalactic space. Tracking these missing baryons is like uncovering a lost piece of the cosmic puzzle that helps explain the universe's mass and structure. Some temperature variations from the Sachs-Wolfe effect seem to form distinct shapes, suggesting hints of something called anisotropy, a term for irregular patterns across the universe. The cosmic microwave background is largely uniform, but these Sachs-Wolfe-induced temperature changes introduce slight directional preferences, creating subtle irregularities. One region of interest is called the axis of evil, a surprising alignment in the CMB temperature data that challenges traditional models of a randomly distributed cosmos. This alignment could hint at unknown structures, or even suggest that the universe has underlying patterns that scientists haven't fully uncovered. Quantum fluctuations from inflation left a cosmic power spectrum recorded in the CMB, and the Sachs-Wolfe effect lets scientists observe these spectral imprints. This power spectrum shows a range of densities in the early universe and reflects the scale of density peaks and troughs left behind by quantum randomness. It's like having a blueprint for the locations where galaxies and voids, empty cosmic spaces, would eventually form. The Sachs-Wolfe effect offers the rare ability to study these imprints, allowing scientists to connect the smallest quantum interactions with the largest galactic structures. The Sachs-Wolfe effect's tiny temperature variations also serve as a cosmic time machine, capturing the universe's state when it was only 380,000 years old. As the universe expanded, photons from this era were stretched across space, embedding early cosmic conditions into the CMB. This snapshot of the young universe captures information about its density, temperature, and even hints of dark matter. Because dark matter doesn't emit light, it's usually invisible. But Sachs-Wolfe variations reveal where dark matter's gravity influenced photon paths, giving scientists an indirect glimpse of the dark matter distribution in early space. Some galaxies and massive clusters cause particularly noticeable temperature dips due to the Sachs-Wolfe effect. This effect helps scientists map large cosmic structures, such as superclusters, massive galaxy groupings. When photons encounter these superclusters, they reveal information about the gravitational pull of these cosmic giants. These temperature fingerprints allow scientists to understand the role of superclusters and how they may influence the cosmic web, the enormous network of galaxies and dark matter that shapes the structure of space. One challenge with observing the Sachs-Wolfe effect is interference from nearby cosmic noise, like dust and radio waves from stars. Dust, for example, can mask the faint temperature changes related to the effect, requiring precise filtering techniques to isolate the Sachs-Wolfe signals. These techniques are critical because even the slightest contamination could distort readings and impact our understanding of dark energy, dark matter, and early universe conditions. The Sachs-Wolfe effect may be used to test predictions of general relativity. Einstein's theory of relativity. The theory of general relativity states that gravitational forces should have a predictable effect on light as it travels across space. The observations of the Sachs-Wolfe effect are in good agreement with these predictions, providing one of the strongest pieces of cosmic-scale evidence for general relativity. We may now grasp the role of gravity in forming the cosmos, thanks to this agreement with Einstein's theories. But any future discrepancies in Sachs-Wolfe data might point to new, unexplored physics beyond general relativity. Dark matter density also impacts Sachs-Wolfe measurements. The effect's strength varies with the amount of dark matter in a region, allowing scientists to indirectly measure dark matter distribution. Dark matter is invisible and doesn't emit light, but its gravitational pull subtly influences the path of CMB photons. This invisible, yet measurable influence helps researchers understand dark matter's distribution across space and its effect on galaxy formation. A calibration tool for telescopes is the temperature map produced by the Sachs-Wolfe effect. Astronomers may utilize the extremely accurate temperature fluctuations to fine-tune the sensitivity of their telescopes. Scientists can now collect more precise data from the cosmic microwave background, CMB, and pick up on even fainter cosmic signals thanks to this calibration. Scientists are able to better trace the history of the cosmos throughout time when they use telescopes that have been fine-calibrated to better see into the far past of the universe. Observing how dark energy impacts the Sachs-Wolfe effect could reveal whether the universe will continue expanding indefinitely or eventually slow down. If the effect changes over time, it could mean that dark energy is evolving, potentially impacting how the universe might end. By tracking these subtle changes, scientists hope to predict if the universe will rip apart or drift into a cold, empty expanse. The Sachs-Wolfe effect doesn't just measure gravity, it provides one of the only ways to observe primordial density fluctuations, the initial seeds from which stars and galaxies grew. These density variations set the stage for cosmic structures and reveal how quantum fluctuations transformed into massive clusters. As space expanded, regions with slight density peaks acted as gravitational wells, attracting matter that formed galaxies over billions of years. This cosmic progression from tiny fluctuations to galaxy clusters highlights the universe's incredible journey from simplicity to complexity. Through these faint temperature changes, the Sachs-Wolfe effect shows the universe's early history, linking ancient quantum activity with present-day cosmic structures. Each variation marks a place where gravity pulled matter together, creating the web of galaxies and voids we see today. X-ray filaments of the Milky Way. The X-ray filaments in the Milky Way are one of the most mysterious phenomena of our galaxy, stretching across the center with intense energy and unusual patterns. These high-energy structures emit X-rays that reveal extreme conditions near the galactic core, particularly around our galaxy's supermassive black hole, Sagittarius A star. Unlike typical remnants of supernovae, these filaments are long, sharp, and aligned along magnetic field lines, suggesting powerful, highly magnetized environments. One unique feature of these filaments is their extremely high energy, which reaches temperatures of millions of degrees Celsius. This is far hotter than the surrounding material in the galaxy, and it suggests that the filaments are connected to intense energy sources. Some scientists believe that this heat might result from high-speed collisions of electrons within the filaments, which release energy in the form of X-rays. These collisions offer a glimpse into the extreme physics occurring at the center of the Milky Way, where forces and temperatures surpass those found anywhere else in the galaxy. The presence of magnetic fields in these filaments is clear. Observations show that they are aligned with the magnetic field lines of the galactic center. These alignments mean that each filament traces a path shaped by magnetic forces, almost like invisible wires that carry energy and charged particles. This magnetism is believed to be strong enough to hold the filaments together, preventing them from dispersing. By studying these magnetic structures, scientists can map out the magnetic environment of the galaxy's core, a place where magnetic fields are far stronger than those found in other parts of the galaxy. X-ray filaments provide the impression of accelerating particles to near-light speeds. These high-speed particles make the filaments act as natural particle accelerators, adding to their mysterious nature. The energy that accelerates these particles likely comes from magnetic reconnection, a process where magnetic field lines merge and release stored energy. This phenomenon is also seen on the Sun during solar flares. But in the galactic center, it happens on a much larger and more powerful scale. Many of these filaments are thought to have originated near Sagittarius A star, the Milky Way's supermassive black hole. Some scientists believe they could be the remnants of past activity from this black hole. Over time, black holes occasionally release jets or flares, which could create these structures in surrounding space. If these filaments are indeed connected to black hole activity, they would be like fossils of past energy outbursts, holding records of events that happened thousands of years ago. These filaments, while clustered near the galactic center, don't stop there. Some stretch far out into the galactic plane, reaching areas rich in molecular clouds. In these regions, they may interact with gas and dust, affecting star formation in nearby clouds. The intense magnetic fields of the filaments could influence the gas in these regions, potentially shaping new stars in the process. By tracing the paths of these filaments, scientists gain clues about how the galactic center affects star-forming regions far from its core. One aspect of these filaments is that they have a consistent width along their entire length. Unlike other cosmic structures that tend to expand or dissipate, the filaments retain a steady thickness. This suggests that they are confined by powerful magnetic fields that maintain their shape. Scientists are still investigating why these fields are so strong and what processes might create them. This uniform width adds to the mystery, as it contradicts typical models of energy dispersal in space. The alignment and arrangement of these filaments also hint at an even larger magnetic structure within the galaxy. Observing the way filaments align with each other suggests that they may be part of a massive interconnected grid of magnetic fields. This grid could span the galactic center, directing the flow of charged particles and affecting how energy moves through space. Such a structure would have a profound impact on the overall dynamics of the Milky Way, potentially influencing everything from star formation to cosmic ray propagation. While the filaments are invisible in optical light, they reveal themselves in hard X-rays, a high-energy form of X-ray radiation. Hard X-rays have more energy than typical X-rays and indicate extremely energetic environments. The detection of hard X-rays from these filaments distinguishes them from other X-ray sources in the galaxy and gives scientists a specific frequency to study. By analyzing these hard X-rays, researchers can learn more about the energy processes that maintain these filaments. The presence of filaments in close proximity to gamma ray, a different kind of high-energy radiation, sources is intriguing. This suggests that the X-ray filaments could be part of even more energetic cosmic phenomena. Gamma rays are usually produced by some of the universe's most powerful events, like black hole jets or supernovae. The presence of both X-rays and gamma rays in close proximity raises questions about whether the filaments and gamma ray sources might be linked, or if they might even be the same events observed at different energy levels. The history of the galactic core may also be shown by the filaments. Sagittarius A's behavior over thousands, if not millions of years, may be explicable by analyzing their internal structure and energy. Consider the possibility that these filaments are flare echoes of the black hole's previous eruptions. This is the view of some scientists. These structures could have been formed by bursts of energy released by the black hole during an active period. Researchers might piece together a history of events in the galactic core by analyzing these echoes, which would reveal information on black hole behavior. Even after extended periods of time, these filaments have shown to be very stable. Despite the high energy within them, they don't appear to disperse or decay quickly. This stability is another clue that they are held together by powerful magnetic fields, which prevent them from breaking apart. Observing this stability gives scientists a rare chance to study long-lasting structures in a place as dynamic and chaotic as the galactic center. The interaction between the filaments and the surrounding cosmic material, such as star-forming regions and molecular clouds, is another intriguing element. It is possible for X-ray filaments to transport energy to areas where they intersect with thick gas clouds. This energy has the ability to seed these clouds with energy, which might alter the circumstances required for star formation. Molecular cloud gas might be compressed into star-forming dense cores by the filament's magnetic fields, according to some scientists. It is impossible to view the filaments, despite their size and energy, without specialist X-ray telescopes, since they are invisible to visible light. Their discovery depended on observatories like Chandra, which can detect the high-energy X-rays they emit. This limitation means that many of the Milky Way's X-ray filaments could still be hidden from us, waiting to be detected by future X-ray missions capable of mapping the entire galaxy. X-ray data reveals that some filaments contain regions of higher density, creating hotspots where energy is even more intense. These spots might mark areas where magnetic reconnection is occurring, a process where magnetic field lines merge and release stored energy. In these hotspots, the release of energy could accelerate particles to near light speed, explaining the intense X-rays emitted. Studying these regions allows scientists to observe cosmic magnetic reconnection, a process also seen on the Sun, but on a much smaller scale. New insights on magnetic field turbulence in the Milky Way may be gleaned from the X-ray filaments. As the filaments pass through turbulent regions, they twist and bend, revealing how magnetic fields interact with other forces. This turbulence impacts the movement of cosmic material, influencing the behavior of gas and dust across the galaxy. By observing these interactions, scientists can learn about the forces that shape the galaxy, as magnetic fields and turbulence play key roles in how material flows through space. Some researchers think that the filaments could be a source of cosmic rays, high-energy particles that travel across the galaxy and reach Earth. If the filaments accelerate particles to high speeds, they might eject these particles into surrounding space, creating cosmic rays. Cosmic rays impact Earth's atmosphere and are a major subject of study, as they can affect everything from satellite technology to climate models. The idea that our galaxy's core could be a source of these rays adds a new layer to the study of cosmic rays. The arrangement of these filaments has also led scientists to suggest that the galactic center may have an organized grid of magnetic fields. The alignment of multiple filaments suggests that they are not randomly placed, but follow a larger structure. This grid could impact how particles and energy move through the galactic core, creating a pathway for charged particles and influencing cosmic magnetic fields. Such a grid would reveal a hidden structure within the Milky Way, one that shapes how energy and matter are distributed. One thing that makes these filaments special in the galaxy is the mix of X-rays, magnetic fields, and high-energy particles. Their presence highlights the complexity and power of the Milky Way's center, an area that is much more dynamic than it appears from Earth. Each filament is a thread in a larger story of how magnetic fields and particle acceleration shape the galaxy. By studying them, scientists hope to uncover the secrets of the galactic center and understand how these structures influence the Milky Way as a whole. In exploring the mysteries of the X-ray filaments, scientists are not just learning about high-energy events, they are also piecing together the history of the galactic center. These filaments act as clues to past black hole activity, changes in magnetic fields, and interactions with surrounding gas and dust. Galactic Cosmic Background Light. The Galactic Cosmic Background Light, GCBL, is a faint, scattered glow that fills space, holding clues from the earliest times when stars and galaxies first formed. Unlike light we see directly from stars or galaxies, GCBL represents the combined remnants of light from countless ancient galaxies. It's a fog that fills the universe, a quiet glow left behind as galaxies evolve and spread through space over billions of years. Each part of GCBL is like a fossilized beam of light, capturing details about how galaxies formed, grew, and eventually faded. One of the most fascinating aspects of GCBL is how it shows the rate at which stars formed in the early universe. By studying its intensity, scientists get a sense of how quickly stars were forming. Different eras saw varying speeds in star formation, and the GCBL gives us insight into those peaks and quiet periods. For example, certain intense bursts of star formation may show up as higher brightness within GCBL, giving us an idea of how much light galaxies produced during times of rapid growth. It's a time machine of light, showing us how active galaxies were during different phases of the universe's history. Unlike the cosmic microwave background, CMB, which is a uniform signal from the Big Bang's afterglow, GCBL comes from galaxies. It spans a wide range of wavelengths, from ultraviolet to visible to infrared. This range reflects the various stages of galactic evolution. Different types of galaxies, from early star clusters to mature spirals, emit light in specific ranges, and GCBL combines them all. It's like a cosmic scrapbook, capturing the many ways galaxies have grown and changed over time. This light budget of the universe, as scientists call it, represents all the energy that stars and galaxies have emitted across time. Sometimes, GCBL is described as the light pollution of the universe. This background glow interferes with observations of fainter, more distant objects. To find the faintest galaxies, astronomers need to separate them from this pervasive background light. Filtering out GCBL is a delicate process, but by analyzing it, scientists can detect clues about faint early galaxies we may never see directly. This hidden structure offers a way to map out parts of the universe that are otherwise too dim to observe. The GCBL's faint light also holds traces from one of the universe's early and crucial phases, the era of reionization. This period began when the first stars and galaxies formed and emitted energy that reionized hydrogen atoms across the cosmos, making space clear and transparent. GCBL carries a kind of echo of this period, revealing how these early stars and galaxies shaped the universe's basic structure. The faint glow of GCBL preserves this information, offering a direct link to when the universe was becoming transparent after the darkness of its earliest stages. Some of GCBL's light may even come from the actions of primordial black holes that formed in the early universe and emitted light as they drew in gas and matter. These ancient black holes produced powerful energy bursts that contributed to the overall background light. Such faint signals give hints about what black holes looked like before galaxies as we know them even existed. Although we don't see the black holes directly, the light they once emitted remains as part of this cosmic background glow. Galaxies themselves can influence the background light when they merge or interact. When galaxies collide, they create bursts of intense starlight. These bursts contribute to GCBL, adding light to the background that remains long after the galaxies have changed shape or merged entirely. Each collision leaves behind a trail of scattered light that eventually becomes part of GCBL, turning the cosmic background into a kind of log of past galaxy interactions. The background light's color and intensity reveal details about what types of stars once filled these galaxies. Just as red giants and blue supergiants have different brightness and color, so too does GCBL reflect these characteristics. If GCBL is particularly red, it may indicate an era dominated by cooler, older stars. A bluer glow might suggest hotter, younger stars. These subtle color shifts provide clues to the universe's star populations at different points in history, showing how types of stars and their frequencies changed. While GCBL acts as a record, it's also a layer of noise that needs to be filtered out to observe the faintest and most distant galaxies directly. Earth's atmosphere also blocks certain wavelengths, making it even harder to isolate GCBL's full range from ground-based observatories. Space telescopes, especially those that can see infrared light, such as Spitzer or Hubble's deep field cameras, have been essential in detecting GCBL with minimal interference. By studying this faint light, astronomers work to piece together images of the universe as it appeared in its youngest days. GCBL is more than a passive glow. It actively interacts with cosmic dust, the thin clouds of particles scattered across space. Cosmic dust absorbs and re-emits light, altering the appearance of GCBL in complex ways. When dust scatters the background light, it shifts the light slightly, producing a kind of hazy glow. This interaction between GCBL and dust changes how intergalactic space appears and can even make certain regions appear brighter or darker. The GCBL also holds answers to what astrophysicists call the missing light problem. Observations suggest there should be more light in the universe than is detected. GCBL could be part of the answer. Its diffuse glow may account for part of the expected light that remains hidden. By studying its faint intensity, scientists are piecing together this puzzle, working to figure out where and how much light may be missing from their initial calculations. Different types of galaxies contribute to GCBL in unique ways, hinting that GCBL might contain signatures from galaxies that are not fully understood or even discovered yet. Theoretical models suggest that starless galaxies, which may emit faint light from residual heat or from light reflected off cosmic dust, could add their glow to the GCBL. These unusual galaxies could be scattered throughout intergalactic space, hard to detect, but contributing subtly to the background glow. The GCBL is affected by a range of high-energy events, from supernovae to gamma-ray bursts, which produce large amounts of light as they occur. The energy from these cosmic events ultimately joins the background glow. Each supernova, with its intense brightness, sends a lasting signature to the GCBL, contributing to a universe-wide record of explosive events. The light from these ancient explosions may now be only a faint whisper within the GCBL, but it helps fill out a picture of the universe's past energy sources. We were able to forecast the GCBL as a component of cosmic light decades before we could witness it directly, which is rather interesting. Models of galaxy formation indicated that such a background light would exist as a byproduct of galactic evolution. Once technology advanced enough, infrared observatories confirmed these predictions. It's a case where theory guided the discovery, a rarity in the hands-on world of observational astronomy. This diffuse glow can also be thought of as the universe's optical depth, a measure of its transparency at different points in time. By examining GCBL, scientists can estimate when the universe was more or less opaque to certain wavelengths. For example, during the early stages of reionization, light couldn't travel freely through space. GCBL captures these shifts, showing how much light was absorbed or scattered at different cosmic epochs. GCBL contains clues about the universe's metal content, which in astronomy refers to elements heavier than hydrogen and helium. Early stars create heavier elements in their cores, spreading them into space through supernova explosions. GCBL holds spectral traces of these metals, indicating the presence of elements like carbon and oxygen in early galaxies. This light gives scientists a direct way to see how metals enriched the universe over time, helping to shape future stars and planets. Cosmic accretion, in which galaxies expand by absorbing gas and dust, is associated with the GCBL. As galaxies pull in material, they often emit excess light that ends up in the GCBL. These emissions, though faint now, provide a historical record of how galaxies grew and evolved over time. Accreting galaxies add to the background glow, creating a layered picture of galactic growth as recorded in light. Even quasars, the intensely bright centers of some distant galaxies, are influenced by GCBL. Quasar light can be slightly altered as it passes through regions filled with GCBL, creating a faint smearing effect. This light distortion changes our perception of quasars' brightness and energy levels. Observing how quasars interact with the background light allows scientists to fine-tune measurements of their power and distance, ultimately refining our understanding of these cosmic giants. In an interesting twist, GCBL could even contain light from cosmic voids, regions in space with very few galaxies. Voids are some of the most challenging areas to observe, but GCBL slightly brightens these dark spots, allowing researchers to study them indirectly. By mapping out the faint background light within these voids, scientists can gain insights into their size, shape, and the distribution of matter in these underpopulated areas. GCBL is sometimes called cosmic twilight, as it represents the faint afterglow of galaxies' light production over billions of years. It's a quiet reminder of the stars and galaxies that once shone brightly, leaving behind a diffuse record of their light. This cosmic twilight illuminates the vast stretches between galaxies, filling the dark spaces with a gentle, almost ghostly glow, a testament to the billions of years of cosmic evolution encapsulated in faint beams of ancient light. Magnetic monopoles. For many years, magnetic monopoles have piqued the interest of researchers. Unlike the common magnets, which always have two poles, these particles would only have one magnetic charge, either north or south. The presence of monopoles, with their one-of-a-kind property, would complete the symmetry in electromagnetic theory and establish an unobserved connection between electricity and magnetism, which has far-reaching consequences. Discovering monopoles might revolutionize our comprehension of magnetic fields by allowing us to think of magnetism as an independent entity. The idea of monopolies first took root when physicist Paul Dirac proposed that even one magnetic monopole in the universe could explain why electric charge appears only in whole units. This concept is known as the quantization of electric charge. On Earth, all charges come in specific amounts. No matter how we try, we can't create a fraction of an electric charge. According to Dirac's theory, if monopoles exist, they would enforce this quantization, showing that electric and magnetic fields are more deeply connected than we realize. Monopoles would be the missing piece in a puzzle that unites electric and magnetic forces, revealing a new layer of order in nature. These hypothetical particles are predicted to be massive. If they exist, monopoles would be much heavier than most other particles, meaning they would move more slowly through space. This high mass would also make them easier to detect if they pass through certain materials on Earth. Unlike ordinary particles, which can zip by quickly and leave little trace, a monopole might interact strongly with a material, carving a distinct path that scientists could identify. This slow, heavy nature would allow them to leave a fingerprint in particle tracks, an unmistakable signature unique to monopoles. The discovery of monopoles would change the way we understand and apply magnetic fields. Imagine the possibility of isolated magnetic islands, regions with single magnetic poles. Currently, every magnet has a north and a south pole, but a monopole would carry just one of these poles. This ability to have an isolated magnetic charge would let scientists explore entirely new ways to use magnetic fields in technology, potentially leading to breakthroughs in how we manipulate and use magnetism in fields ranging from electronics to medical devices. Monopoles would be extremely stable particles with no known natural decay mechanism. If they formed in the early universe, they would likely still be around today. This stability means that monopoles could be relics from the universe's earliest moments, surviving through cosmic inflation and the subsequent cooling of space. Any monopoles that were created would remain intact, providing direct clues about conditions just after the Big Bang. This resilience makes them not only a potential key to understanding magnetism, but also a window into the universe's ancient history. To detect these elusive particles, scientists have turned to extreme environments. Some experiments look for monopoles in places with minimal interference, like deep underground or in polar ice, where background noise is low. These remote settings provide a chance for monopoles to be trapped or preserved over time, protected from other particles and forces that might otherwise disturb them. Researchers hope that these pristine environments could hold the answer, with monopoles lying dormant, waiting to be discovered. Superconductors may also hold clues about monopoles. Certain theories suggest that monopoles could create unusual effects in superconducting materials. Superconductors, which conduct electricity without resistance, may react to monopoles in ways that are entirely different from regular particles. For example, monopoles might cause stable magnetic vortices in the superconductor, creating a kind of controlled magnetic whirlpool. These effects would offer a way to study monopoles in a laboratory setting, giving scientists a closer look at how these unique particles behave in specific materials. The existence of monopoles would reveal hidden symmetries in physics, balancing electric and magnetic charges in a way that our current models can't. Right now, we have no equivalent for the magnetic charge in our understanding of particle physics. But with monopoles, this symmetry would be complete, giving us a reason to think that electric and magnetic forces are two sides of the same coin. This balanced symmetry would rewrite certain principles in physics, hinting that our universe follows a more orderly structure than previously thought. Monopoles could act as isolated magnetic points, unlike anything we've observed in ordinary materials. Unlike regular magnets, which always come with both poles, monopoles would function as independent magnetic charges. In this sense, they would behave as magnetic islands, offering a way to study how magnetism behaves in complete isolation. This unique form of magnetism would have far-reaching implications, opening up entirely new ways to manipulate magnetic fields for science and technology. It has been suggested in certain theoretical models that monopoles may affect the inherent stability of matter. Scientists think they may influence matter stability as a whole through their potential role as catalysts for proton decay, an extremely rare occurrence. Monopoles may be able to alter the basic behavior of particles if they are able to catalyze proton decay. This finding would be revolutionary because it would show a property of matter's stability, which can only be known when monopoles are present. Light and electricity might potentially be impacted by monopoles. Some hypotheses suggest that monopoles might modify the vacuum's characteristics, perhaps altering the interaction between space and light. As an example, monopoles have the potential to slightly change the speed or behavior of light, which might uncover new features of the fabric of the cosmos. Light, energy, and magnetism are all interrelated, and these interactions might reveal novel phenomena that are unique to monopolies. Quantum computing is another area where monopolies could play a transformative role. Due to their isolated magnetic charges, monopoles could perform specific functions within quantum systems that require precise magnetic control. These unique properties might make monopoles valuable in quantum computing, where researchers constantly seek new ways to control particles at extremely small scales. Monopoles could enable new types of quantum computing operations, taking advantage of their unusual magnetic properties to expand the capabilities of quantum technology. Experts have used man-made spin-ice crystals to study monopole-like behavior. Scientists have noticed behavior similar to magnetic monopoles in these man-made materials. Spin-ice crystals have comparable dynamics to monopoles, providing a model for the behavior of hypothetical monopoles. The controlled environment provided by spin-ice allows scientists to investigate monopole qualities in more depth than would be possible with real monopoles. The results of these trials provide light on the possible interactions of monopoles in more complex systems. Using antiquated minerals is another novel strategy for discovering monopoles. The ubiquitous layer-forming material mica has the potential to maintain the tracks left behind by monopoles. Investigating old mica deposits may provide fossilized remnants of monopoles that existed millions of years ago, according to some scientists. The approach of conducting a geological search for monopoles is novel. It involves handling the particles as artifacts from the planet's ancient history. If monopoles formed in the universe's earliest moments, they would essentially be fossils from the Big Bang. These particles would hold clues about the environment just after the universe began, potentially surviving the violent conditions of cosmic inflation. The idea that monopoles might be relics of the Big Bang means they could provide direct evidence of what happened in the universe's first moments, offering a rare glimpse into events that shaped everything we observe today. The magnetic behavior of monopolies would also differ from that of any known particle. If monopoles exist, they could create circular or looped magnetic field lines, unlike the typical straight-line field structures we see with regular magnets. This unique magnetic interaction would help scientists study magnetic fields in a completely new way, revealing how they might behave when subjected to isolated magnetic charges. These field structures would be unlike anything observed with ordinary magnets, providing a distinct signature of monopolies. Their existence would force a change in the core equations of electromagnetism. Maxwell's equations, which describe the relationship between electric and magnetic fields, currently lack any mention of monopoles. If monopoles were discovered, physicists would need to rewrite these equations to account for their presence, transforming our fundamental understanding of electromagnetism. This change would bring magnetic fields to equal footing with electric fields, fully integrating both into a unified framework. Searching for monopoles through cosmic ray detectors could identify the unique energy patterns they leave behind. By watching for rare particle events that match monopole signatures, researchers hope to identify these particles amidst the stream of other cosmic rays. Specialized cosmic ray detectors could capture monopole energy signatures, offering a new avenue in the search for these rare magnetic particles. There's also a possibility that meteorites, which have traveled through space for billions of years, could hold trapped monopoles. As meteorites are ancient cosmic material, they might contain monopoles that have been preserved since they were created. Analyzing meteorites could reveal traces of these particles, providing another method for studying monopoles without direct observation in laboratories. In quantum field theory, monopoles are represented in diagrams known as Feynman diagrams, where they interact with other particles in unique ways. These diagrams illustrate how monopoles might influence particle dynamics, creating loops and exchanges unlike those seen with ordinary magnetic fields. By studying these theoretical interactions, scientists gain insights into how monopoles could behave in high-energy environments, even before they're observed directly. From their stability and potential influence on light to their distinct place in quantum computing, monopoles open doors to new physics, offering insights into the nature of magnetism and symmetry. The spin-flip transition. The spin-flip transition is one of the most interesting signals in the universe, emerging from the unique behavior of neutral hydrogen atoms. This signal occurs when the electron in a hydrogen atom flips its spin to match that of its proton. As small as this change might seem, it releases a precise wavelength of 21 centimeters, creating a signal that can travel vast distances in space without interference. Known as the 21 cm line, this wavelength is central to radio astronomy, revealing some of the universe's hidden structures and stories. Hydrogen's spin-flip transition is exceptionally rare. For any single hydrogen atom, it might only happen once every 10 million years, yet this faint signal is widespread in space. Neutral hydrogen, the most abundant element in the universe, fills galaxies and the space between them, and wherever it exists, the 21 cm line might be detected. Its faintness makes it difficult to observe directly, but when enough hydrogen atoms emit this wavelength, it becomes possible to map the structure of hydrogen gas across the cosmos. This is especially valuable because neutral hydrogen doesn't emit visible light, making the spin-flip transition one of the only ways to see it in its natural state. The 21 cm line allows scientists to trace hydrogen back to the earlier stages of the universe. Unlike light from stars, which changes and fades, the 21 cm signal can travel undisturbed, capturing a record of hydrogen as it was billions of years ago. This makes it a powerful tool for looking back to the universe's dark ages, a period before stars even formed. During this time, hydrogen was spread across space, untouched by starlight or other cosmic events. The 21 cm line is one of the only signals that can reveal these early eras, providing a view into times when space was filled mostly with cold, neutral hydrogen. Scientists can also understand when and how hydrogen in the universe transformed from neutral to ionized, a period called cosmic reionization. When the first stars and galaxies formed, their intense light began to ionize hydrogen atoms, stripping away electrons and making space more transparent. The 21 cm line allows scientists to track these changes, showing how the first stars influenced their surroundings. By studying these patterns, astronomers can pinpoint regions where reionization occurred, effectively mapping out when and where the first galaxies came to life. The 21 cm line also acts as a cosmic thermometer. Nearby cosmic events, like supernovae or active galaxies, which release a lot of energy, affect the temperature of hydrogen gas. Details on the heating or cooling processes of gas across space are revealed when this energy warms hydrogen gas, which modifies the brightness of the 21 cm signal. Scientists learn more about the cosmic events' effects on their environment and the energy flow inside galaxies through these temperature fluctuations. This information does double duty. It maps the gas and provides clues about the processes that mold galaxies across time. The spin-flip transition can also reveal massive structures like the cosmic web, a network of hydrogen filaments connecting galaxies and clusters across space. This network is like a vast spider web, made mostly of dark matter and hydrogen, that stretches across the universe. By tracking the 21 cm line, astronomers can see how hydrogen clusters into filaments and voids, creating this web-like structure. The cosmic web forms the skeleton of the universe, shaping where galaxies form and how they are connected, giving scientists a direct look at the grand architecture of space. It is only neutral hydrogen, not ionized hydrogen, that emits the intense 21 cm line. This signal can no longer be emitted by hydrogen in an ionized area, which usually occurs in the vicinity of young, hot stars. This causes holes to appear in the 21 centimeter image, which may be used to pinpoint areas where stars are born. By tracking the disappearance of the 21 cm signal, astronomers may pinpoint regions of active star formation. This is because the radiation emitted by newly formed stars ionizes hydrogen in the surrounding area, causing the 21 cm signal to fade and identifying regions of galactic expansion. When investigating the spin of galaxies, the 21 cm line is also very helpful. By observing hydrogen in and around galaxies, scientists can map out how galaxies rotate. This rotation data is vital for understanding how galaxies distribute mass, including the mysterious dark matter that influences their movement. Dark matter doesn't emit light, but it has mass, which affects how hydrogen moves. The 21 cm line indirectly shows where dark matter likely exists by tracking hydrogen's rotation, revealing hidden mass within galaxies that can't be seen any other way. Even on cosmic scales, the 21 cm line serves as a reliable distance marker. As the universe expands, light from distant objects stretches, a phenomenon known as redshift. The 21 cm line experiences this redshift as it travels, allowing astronomers to calculate the distance of hydrogen clouds across space. Each redshifted 21 cm signal provides information about how far away the hydrogen is, and by extension, how far back in time it originates. This allows scientists to build a timeline of cosmic history based on the distance and age of hydrogen clouds observed at different redshifts. Surprisingly, the 21 cm line is also a valuable tool for detecting the cosmic web and understanding large-scale cosmic structures. By mapping out hydrogen across space, the 21 cm signal reveals where vast cosmic voids and dense clusters lie. Cosmic voids, which are regions with very few galaxies, stand out due to the lack of hydrogen emissions, while clusters with many galaxies create dense signals. This gives astronomers a three-dimensional map of where galaxies, voids, and clusters exist, helping them see the grand-scale structure of the universe. Even the evolution of galaxies may be seen in the 21 cm signal. Over time, galaxies undergo cycles of star formation, gas depletion, and gravitational interactions. The 21 cm line allows scientists to monitor these processes by tracking hydrogen gas across galaxies. By studying how hydrogen clumps, spreads, or even disappears, researchers can see which galaxies are actively forming stars, which are losing gas, and which may be merging with other galaxies. This long-term view shows how galaxies change over billions of years, providing insight into the life cycles of galaxies across the universe. Cosmological magnetic fields may also affect the 21 cm line, which is an intriguing fact. As hydrogen gas interacts with magnetic fields, it can affect the signal, allowing scientists to map the structure of magnetic fields across space. Magnetic fields are otherwise invisible, but play an important role in galaxy formation and star formation. By observing how these fields influence the 21 cm line, astronomers can indirectly trace their structure, seeing how they affect hydrogen distribution and galactic evolution. The fact that it may be observed without space observatories is one of the 21 cm line distinguishing features. The 21 cm line is detectable by radio telescopes on Earth because, unlike other wavelengths, it is unaffected by Earth's atmosphere. Because it is easily accessible, the spin-flip transition is a potent instrument for studying hydrogen from Earth, which helps conserve resources and permits ongoing monitoring of hydrogen in space. In certain regions, neutral hydrogen absorbs background radiation instead of emitting light. This creates a unique feature called the 21 cm absorption line, which appears as a dip in the spectrum. Scientists use this absorption line to measure the density and temperature of hydrogen clouds, revealing properties of cosmic gas that can't be seen through emission alone. By studying these absorption lines, astronomers gain another layer of insight into hydrogen's role in cosmic structures. The spin-flip transition has played a pioneering role in large-scale cosmic surveys. These surveys, which map huge portions of the sky, rely heavily on the 21 cm line to track hydrogen distribution. Early radio astronomy surveys used this line to build the first detailed maps of the Milky Way and nearby galaxies. Modern surveys have expanded to map hydrogen in the farthest reaches of space, creating a clearer picture of the universe's hydrogen content and structure. The 21 cm line can also be helpful in the search for dark galaxies and other shadowy objects. Optical telescopes cannot detect dark galaxies because they are believed to consist primarily of hydrogens. But they can still produce the 21 cm signal, so scientists can find them through radio measurements, because they contain hydrogen. Because of this, we now know more about the diversity of galaxies in the cosmos and have found galaxies that were previously unknown. Beyond individual galaxies, the 21 cm line provides clues about larger cosmic structures, including galaxy clusters. These clusters, which contain hundreds or thousands of galaxies, attract vast amounts of hydrogen gas. By studying how hydrogen moves within clusters, astronomers can map out these regions, showing where galaxies are likely to collide, merge, or grow. This mapping reveals how galaxy clusters evolve and how their gravitational pull shapes the universe's structure. Using the 21 cm line, scientists are even testing hypotheses concerning the birth of the cosmos, which is just astounding. Some models of the early universe predict specific patterns in hydrogen's density and distribution, which can be compared against actual 21 cm observations. By seeing how well these patterns align, scientists can test if current models of cosmic evolution match observed data. If significant differences emerge, it may suggest new aspects of physics or cosmic processes that haven't been accounted for yet. Sound waves from the early cosmos, known as Barion acoustic oscillations, BAOs, may be better understood with the help of the 21 cm signal. These waves left density patterns in cosmic matter, creating ripples that later influenced galaxy distribution. The 21 cm line lets astronomers detect these patterns by tracing hydrogen clumps, providing one of the most direct measurements of BAOs and helping us understand the origins of cosmic structure. The 21 cm line provides an observational window into primordial hydrogen clouds, which are clouds devoid of any influence from stars or galaxies. These clouds give a glimpse into the universe's most pristine gas, untouched by the processes that shape galaxies. By observing these clouds, scientists can see what hydrogen looked like in its purest state, adding a valuable piece to the puzzle of cosmic history. Each of these insights from the spin-flip transition shows how hydrogen, the simplest atom, continues to shape our understanding of the universe. Whether mapping galaxies, measuring distances, or testing cosmic theories, the 21 cm line is a constant beacon, revealing the structure and history of the cosmos in ways that are both profound and essential to our understanding. Odd radio circles, AURCs. Odd radio circles, AURCs, have puzzled astronomers since their recent discovery in 2019. These circular formations, visible only in radio wavelengths, are gigantic in size, about 1 million light-years across, 10 times larger than the Milky Way. Yet despite their vastness, they remain undetectable in visible light, infrared, appearing only in the radio spectrum, which immediately sets them apart from any known cosmic structures. What makes AURCs even more puzzling is that they are found in seemingly empty regions of space, far from the galaxies and stars we usually associate with radio emissions. Unlike pulsars, supernova remnants, or active galactic nuclei, which emit strong and concentrated radio signals, AURCs emit faint, diffuse radio waves, and they do so with a nearly perfect roundness. Few cosmic objects are this circular, especially on such a large scale, and the precise symmetry of AURCs raises intriguing questions about their origin. Some scientists believe AURCs could be the result of massive shock waves created by ancient cosmic events, such as collisions between supermassive black holes or powerful galaxy mergers. These shock waves could expand outward in space, creating a circular shell of radio emission. But this theory, though interesting, has no direct observational evidence. For now, AURCs remain strange, with no clear explanation of the energy source that could drive such a massive expansion across intergalactic space. The possibility that AURCs are the lingering effects of activity in faraway galactic centers is another theory. Occasionally, enormous particle jets or outflows are released by galaxies that contain supermassive black holes in their cores. We now see circular waves known as AURCs, because these jets might have produced them if they had interacted with the stuff around them. But much like previous theories, this one doesn't provide any evidence of similar structures found in the cosmos, so researchers are still left with more questions than answers. Fascinating details about AURCs is that they are found exclusively in radio wavelengths. Observations in infrared light show no corresponding structures, even in deep sky surveys. This radio-only presence means AURCs are challenging to study, as their faint radio waves require long periods of observation with sensitive telescopes. Yet, radio telescopes like ASCAP in Australia and the meerkat in South Africa are helping scientists capture images of these mysterious circles, though their radio-only visibility continues to defy explanation. It is intriguing because certain orcs appear to have dim galaxies at their centers, leading some to speculate that these galaxies might play a role in the development of orcs. These galaxies may have been the sites of violent events that triggered the circular waves known as orcs. In such case, the enormous radio waves seen as orcs would actually represent the leftover energy from previous outbursts. Although this idea establishes a connection between orcs and galactic processes, it does not explain how such weak radio circles may emerge in isolated parts of space. Orcs come in three general shapes: single rings, double-ringed structures, and irregular forms. The double-ringed orcs suggest that some orcs might expand over time, with one ring marking an older stage and the other a newer one. These expanding orcs hint at shockwave activity, possibly from galaxy interactions or black hole collisions. The double-ringed structures in particular might represent synchronized expansions, suggesting that some orcs were formed by cosmic events with enough energy to produce several shockwave rings over time. One question that stands out is the energy required to create an orc. Given their massive size, the amount of energy needed to form one of these structures would be enormous, possibly equivalent to thousands or even millions of supernovae. But without a clear energy source, scientists can only guess at what could power such formations. Theories range from unknown types of cosmic explosions to interactions with unseen forces. Despite their large size, orcs are incredibly rare, with only a few examples detected to date. This rarity has led some astronomers to suggest that they may form only under very unique cosmic conditions, such as specific alignments of galaxies or rare galactic events. The limited number of orcs observed so far may also mean that they are short-lived phenomena, or that they fade quickly in cosmic terms, appearing briefly in radio surveys before disappearing. Some researchers have proposed that orcs could be gravitationally lensed structures. In gravitational lensing, light bends around massive objects such as galaxy clusters or black holes, creating rings or arcs. If orcs were lensed radio signals from distant objects, they might look like circles from our point of view. However, this theory doesn't match the lack of corresponding optical, suggesting that orcs may indeed be physical structures rather than distorted images of distant objects. The biggest challenges to understanding orcs is their faintness. Unlike pulsars or quasars, which emit powerful radio waves, orcs emit low-intensity signals that make them difficult to detect, even with modern telescopes. The ASKP and meerkat radio arrays, which have high sensitivity, were essential for detecting orcs, as they can capture faint radio sources that older radio telescopes might miss. Future radio surveys may reveal more orcs, providing additional data to help unravel their origins. Lack of polarization in orc radio signals is another mystery. Polarization in radio waves often indicates the presence of magnetic fields or particle interactions, yet orcs show little to no polarization. This could mean that orcs are not influenced by strong magnetic fields, or that the magnetic properties of their environment are different from other cosmic sources. The lack of polarization provides a hint, but it's still unclear what it tells us about ORC formation. One of the most widely held beliefs among scientists is that orcs may be connected to the activity of black holes. Expulsions from supermassive black holes, known as jets or outflows, can transport energy to regions distant from the center of the galaxy. The circular shape of an orc might be better explained if it originated as a wave of energy emanating from a black hole. It is still conjectural that orcs are involved in black hole activity, as there is no proof of black hole interactions inside any orc. Some scientists think that orcs might form in galaxy clusters, where many galaxies are clustered together, interacting gravitationally and magnetically. The dense environments of galaxy clusters provide plenty of raw material and energy for cosmic interactions, possibly creating the ideal conditions for orc formation. Observing how orcs align with galaxy clusters may reveal whether their formation depends on these dense, active regions. Unique feature observed around certain orcs is a faint halo of radio emission extending beyond the primary circle. This faint halo could be a sign of extended magnetic fields or particles spreading outward from the main orc structure. The presence of this halo suggests that orcs may be more complex than simple rings. possibly with layers or zones of varying energy and density. Though AUKs are similar in shape to known radio galaxies, which emit jet-like structures from their centers, they don't seem to fit this classification. Radio galaxies show clear jets and cores, whereas AUKs lack these characteristics. Their distinct appearance suggests that AUKs may represent an entirely new type of radio object, unrelated to traditional radio galaxies, and possibly unique to a specific cosmic event or process. The expansion of some AUKs appears to be synchronized, with each layer or ring expanding at a similar rate. This synchronized expansion points to a single event or mechanism affecting each AUK in a uniform way. Such coordinated behavior is unusual for cosmic structures and raises questions about whether AUKs might be echoes of cosmic events, like ripples from a pebble thrown into a pond, expanding outward with each wave. Observations also reveal that AUKs lack visible rotation, unlike other circular cosmic objects such as galaxies. This absence of rotation may narrow down their origins, as most spinning objects in space have clear rotational signatures, while AUKs appear stable and static. This unusual stability, combined with their circular shape, adds another layer of mystery to their formation. Quite a few AUKs have been located billions of light-years away, suggesting that they originated from very old cosmic events. This vast distance suggests that if AUKs are linked to cosmic events, those events were significant enough to produce a detectable effect across billions of years. AUKs might hold clues to early cosmic events or unknown processes that occurred long before the Milky Way even formed. AUKs may represent an entirely new class of astronomical objects, distinct from galaxies, stars, or other known cosmic structures. If AUKs are indeed a new class, their discovery hints at other potential unknown structures in the radio universe that we have yet to observe. This realization opens up exciting possibilities for radio astronomy, as AUKs may be just the beginning of discovering a hidden radio cosmos. Some astronomers have suggested that AUKs could act as markers for galaxy evolution. The faint circular waves might reveal points in time when galaxies transitioned or changed. For instance, AUKs could mark phases of galaxy outflows or interactions that impact their development. By tracing AUKs and studying their alignment with galaxies, scientists might learn more about how galaxies evolve and what events trigger large-scale structural changes. Odd radio circles might seem quiet and mysterious, but each one represents a puzzle piece in understanding the radio universe. As astronomers continue to study AUKs, they aim to unlock the secrets they hold about massive cosmic events, the behavior of galaxies, and possibly even unknown physical processes. These circles remind us that even in the vast stretches of space, unknown phenomena await, sparking curiosity and expanding the boundaries of what we know about the universe. Red spiral galaxies. Red spiral galaxies are unusual structures standing out in a universe where most spirals glow in shades of blue. Typical spiral galaxies get their blue color from hot young stars that form continuously in their spiral arms. But red spirals are different. Their red hue reveals a population of older, cooler stars. Star formation in these galaxies has nearly stopped, or quenched, leaving behind a galaxy filled with aging stars. This unusual combination of a spiral shape with a red color makes red spiral galaxies rare and unique. One defining feature of red spiral galaxies is their lack of gas, which is essential for star formation. Blue spirals, with plenty of gas, create new stars, giving them their bright, youthful glow. Red spirals, on the other hand, have either lost or used up most of their gas, leading to the absence of young stars. This lack of gas is a primary reason these galaxies are quenched. Without enough gas, they can't replenish their star population, which leaves them with an older, redder appearance. This gas depletion might occur over millions of years, slowly shutting down the galaxy's ability to create new stars. In addition to being low on gas, red spirals tend to have less dust compared to blue spirals. Dust plays a key role in star formation by helping cool down gas clouds, allowing them to collapse and form stars. With less dust, red spirals have fewer places for new stars to form. This lack of dust is another factor in their red and dead nature, and it hints that red spirals have gone through processes that depleted their dust reserves as well as their gas. Without these critical materials, these galaxies grow older, without the bright young stars that would normally keep them active. Red spirals are often found in dense environments, like galaxy clusters, where they interact with other galaxies. Galaxy clusters are full of gas, dust, and other galaxies, all of which can influence a galaxy's development. Some scientists believe that these dense environments are crucial to the formation of red spirals. In clusters, red spirals may experience strangulation, a process where they lose their gas supply due to gravitational interactions with nearby galaxies. These interactions might strip away the gas in the outer regions of red spirals, starving them of the fuel needed for star formation. A theory suggests that red spirals are formed through a process called galaxy starvation. In this scenario, the gas inflow that would normally replenish a galaxy's reserves is cut off. Over time, the galaxy uses up its internal gas, leaving it with little to create new stars. This slow process can take billions of years, eventually turning a once blue star-forming spiral into a red spiral. Starvation could occur when a galaxy enters a cluster and encounters hot, dense gas that prevents fresh gas from flowing in. As the galaxy loses its ability to form stars, it gradually fades into a reddish, inactive state. The redness of these galaxies isn't just due to their lack of new stars. It's also a result of the presence of older, cooler stars. In a blue spiral galaxy, young, hot stars dominate the color, but red spirals lack these young stars. Instead, they are filled with stars that are several billion years old. These older stars emit more red and yellow light than blue, giving the galaxy an overall red appearance. The aging stellar population of red spirals is a clue to their long history, indicating they've gone through phases of star formation before gradually shutting down. Compared to blue spirals, red ones also have bigger bulges in the middle dot. This suggests they may have evolved differently or gone through different growth phases. The central bulge is a dense region of stars near the galaxy's center, and in red spirals, it's often more prominent than in blue ones. This feature might indicate that red spirals once had an active period where they formed a large number of stars in the core, followed by a gradual reduction in star formation in the outer arms. While blue spirals are known for their rotation, some red spirals rotate more slowly. This difference in rotation might be due to gravitational interactions with nearby galaxies, which could alter the galaxy's momentum. These interactions could slow down a red spiral's rotation over time, further changing its structure and reducing its ability to form new stars. The slower rotation of red spirals may also influence how gas and dust settle within the galaxy, impacting its ability to maintain a youthful star population. Despite their inactivity in star formation, red spirals retain their distinct spiral arms. This is unusual since spirals often rely on new stars to keep their structure visible. In a typical blue spiral, star formation in the arms continuously reshapes the spiral pattern, but in red spirals, the arms appear frozen. The fact that red spirals retain their arms, even without active star formation, suggests they have a stable structure, possibly due to stronger internal gravitational forces. Red spirals may also offer clues about conditions in the early universe. Some scientists think that red spirals could have formed in ways similar to early galaxies, with star formation happening quickly before slowing down. This early quenching would leave them with older stars and a red color. Studying these galaxies might reveal insights into how ancient galaxies evolved before stabilizing into more static forms. Potential future for red spirals is a transition into lenticular galaxies, which have a disc-like structure but lack spiral arms. Lenticular galaxies are common in clusters and are known for their lack of star formation. As red spirals age, they may gradually lose their arms and become lenticular, transitioning into a more featureless shape over time. This process of arm fading could represent the final stage in the evolution of red spirals, as they lose their defining structure and become part of the more common lenticular population. The environments of red spirals suggest they have gone through changes caused by outside forces, like interactions with nearby galaxies or the hot gas in galaxy clusters. These influences might be why red spirals are more common in clusters than in isolation. Without the influence of other galaxies, spirals in less dense regions retain their blue color and active star formation. The presence of red spirals in clusters points to the idea that galaxy interactions play a significant role in shaping their color and activity levels. Red spirals are also believed to have higher metal content than blue spirals. In astronomy, metals refer to elements heavier than hydrogen and helium, which are produced in stars. Older stars in red spirals create more metals over time, enriching the galaxy. As star formation stops, these metals build up in the remaining stars, contributing to a higher overall metal content. This metal-rich composition is another indicator that red spirals have an older population of stars that have gone through several life cycles. While red spirals may seem red and dead, they still have a rich internal structure. Many contain dense, compact stellar cores where star formation was once intense. These cores are filled with older stars that have settled into a stable structure. In the past, these regions likely hosted a high rate of star formation before the galaxy's gas reserves ran out. Today, these cores remain as remnants of a more active past, giving red spirals a layered history of growth and decline. The mystery of red spirals is deepened by their relatively quiet environments. Unlike galaxies that have experienced major mergers or collisions, red spirals appear undisturbed. They lack the distortion seen in galaxies that have undergone recent mergers, which suggests they have evolved slowly over time. This lack of recent disturbances means they may represent a more peaceful form of galaxy evolution, where changes happen gradually rather than through violent interactions. Magnetic fields may also play a part in the life of red spirals. Strong magnetic fields can limit how gas flows into a galaxy, potentially reducing star formation. In red spirals, magnetic fields might have played a role in shaping their structure and limiting gas inflow, which would contribute to their low star formation rates. Magnetic influences may create stability within these galaxies, helping maintain their spiral shape without active star formation. Even though star formation has nearly ceased, some red spirals still contain remnants of dust in rings around their central bulges. This dust may be left over from past star-forming events and could represent the final traces of activity in these quiet galaxies. The presence of these dust rings hints at a history where star formation was once possible before the galaxy transitioned into a more inactive phase. Red spirals provide a snapshot of galactic evolution, showing what might happen when a once active galaxy runs out of fuel. They highlight the importance of environment, internal structure, and star population in shaping a galaxy's destiny. These galaxies serve as reminders that not all spirals stay blue and active forever. Some evolve into red, quiet forms that slowly fade with time. Through their unique characteristics, red spirals add another layer to the mysteries of the universe, showing that even familiar structures like spirals can hide surprising and unexpected histories. The Intergalactic Whispers. The intergalactic whispers, also known as primordial echoes, are faint, low-frequency signals drifting through the space between galaxies, hinting at secrets hidden in the cosmic void. Unlike signals from stars or galaxies, these whispers don't have a clear source. They're too weak and too diffuse to be easily traced to a single origin, and yet they hold clues to some of the most elusive mysteries of the universe. Some scientists believe these whispers might carry information dating back to the universe's earliest days, making them potential records of cosmic history. As these whispers travel through space, they stretch due to cosmic expansion, giving scientists a way to measure how quickly the universe has grown over time. This stretching, known as redshift, happens to all forms of light as they move across expanding space. For intergalactic whispers, this effect is especially pronounced because they've traveled vast distances. The redshifted whispers act as a kind of cosmic clock, allowing scientists to estimate their age and track how the universe's expansion has affected signals over billions of years. The interaction between these whispers and intergalactic plasma, a heated ionized gas that covers the space between galaxies, is one of the most interesting parts of this phenomenon. The frequency of the whispers indicate that they traverse this plasma, which therefore influences their trajectories. Plasma isn't uniformly distributed over space. It tends to condense in certain regions and diffuse in others, frequently lining up with cosmic filaments. Whispers are molded by these gaps and clusters as they pass through the medium, leaving behind tiny traces of the cosmic web. Scientists are able to map areas that would be undetectable without the imprints carried by each whisper, as it travels through plasma. The faint nature of intergalactic whispers makes them difficult to detect, often blending into the background noise of space. To pick up these signals, scientists rely on sensitive radio interferometry, which combines data from multiple radio telescopes to boost sensitivity. This advanced technique helps filter out the noise of more powerful signals, allowing the whispers to emerge from the background. Even with this approach, only the largest and most powerful radio telescopes can detect them, revealing the immense challenges involved in studying these faint intergalactic signals. Some scientists wonder if the whispers could be echoes from ancient supernovae, explosions powerful enough to send shockwaves through intergalactic space. If these explosions happened far enough back in cosmic history, their faint remains could still be drifting between galaxies. These remnants would be barely detectable, and they'd interact with intergalactic matter, leaving behind whispers that could tell the story of violent events from the early universe. Each whisper might, therefore, be a tiny echo of a long-gone star, a signal that's crossed cosmic distances and eons to reach us. In some cases, the whispers appear to line up with galaxy clusters, areas where many galaxies are packed tightly together. Galaxy clusters are busy places with galaxies constantly interacting and exchanging material. It's possible that the whispers are remnants of these interactions, traces of the gas and dust thrown off as galaxies collide. If this is the case, intergalactic whispers might act like clues, hinting at the ongoing dance of galaxies and their complex interactions. By mapping out these whispers, scientists hope to get a better picture of how galaxies interact on a grand scale. The whispers may also be influenced by weak magnetic fields that thread through intergalactic space. Though these magnetic fields are much weaker than those found in galaxies, they still affect particles and signals passing through. The whispers' paths can be slightly bent or shifted by these fields, helping scientists understand how magnetism is spread through space. These magnetic fields are remnants of ancient cosmic processes, and by tracing their influence on the whispers, researchers hope to map out the magnetic history of the cosmos. Some theorists have suggested that intergalactic whispers might hold traces of exotic particles, such as axions. Axions are hypothetical particles that are believed to interact only weakly with other matter, making them incredibly difficult to detect. If these particles do exist, they could alter the whispers in subtle ways, causing faint shifts in frequency or intensity. By analyzing the whispers, scientists might get an indirect glimpse of these elusive particles, offering a new way to explore forms of matter that lie beyond our current understanding. The possibility that intergalactic whispers are leftover cosmic sound waves from the early phases of the cosmos is an intriguing notion. When the cosmos first came into being, it was a dense, hot plasma rife with pressure and density fluctuations caused by sound waves. These waves eventually diminished, leaving behind only weak traces as the cosmos became larger. It is speculated by some scientists that these sound waves may continue to reverberate as low-frequency signals, illuminating the structure and density of the early universe in a subtle way, almost like whispering. Intergalactic whispers might also help answer questions about the universe's missing matter. Observations suggest there is more matter in the universe than we can see in stars and galaxies. Some of this missing matter could be spread out in intergalactic space, invisible to telescopes but detectable through its effects on faint signals like the whispers. By studying variations in whisper strength and frequency, scientists hope to uncover where this hidden matter lies, helping to complete the cosmic map. Unusual features of the whispers is that they show very little polarization, unlike many other signals from galaxies. Polarization occurs when signals align along specific directions, often influenced by strong magnetic fields. The lack of polarization in these whispers suggests that intergalactic space has weaker magnetic fields than galaxies, which in turn affects how energy flows through these regions. This lower polarization might mean that the whispers are relatively pure, unshaped by the forces that usually impact galactic signals. Intergalactic whispers are thought to pass through cosmic voids, enormous empty regions of space where there are few galaxies and almost no matter. These vast voids are like cosmic deserts, and the whispers seem to weaken as they move through them. Studying how whispers behave in these voids might help scientists learn about the properties of cosmic nothingness, as well as the subtle forces that might still be at play in these empty regions. The whispers' interactions with voids reveal faint but essential details about the large-scale structure of the universe. The low-energy nature of the whispers presents a mystery about their origins. Unlike bright, high-energy events, these whispers are faint and persistent, suggesting they come from subtle, widespread sources. This low energy could indicate that they aren't produced by singular, explosive events, but rather by ongoing, faint processes spread across vast distances. These processes might include low-energy cosmic rays, gentle interactions between particles, or even energy exchanges within the cosmic web. Cosmic winds, powerful streams of gas and particles flowing out of galaxies, might also play a role in shaping the whispers. These galactic winds can blow material far into intergalactic space, interacting with existing particles and possibly influencing the whispers as they pass through. By studying how the whispers change near regions with strong cosmic winds, scientists hope to learn more about the influence galaxies have on their surroundings, even beyond their visible edges. The whispers could even carry evidence of the cosmic reionization period, a time when the first stars ignited and began to ionize hydrogen in the universe. During reionization, intense radiation from early stars and galaxies transformed the gas in space, making it more transparent. If the whispers traveled through reionized areas, they might carry faint signatures from that time, allowing scientists to study this major phase in the universe's development. By analyzing these signatures, researchers could gain insights into the first stars and the changes they caused across intergalactic space. In some cases, the whispers' paths might be slightly bent by gravitational lensing, a phenomenon where massive objects bend the path of light. Gravitational lensing often magnifies or distorts light from distant objects, and if these whispers are affected by unseen masses, they could reveal hidden cosmic structures. This subtle bending might indicate massive, invisible structures between galaxies, providing indirect clues to what's lurking in the space between galaxies. Another curious effect of these whispers is their interaction with cosmic filaments, the vast bridges of matter connecting galaxies across space. The whispers may align with these filaments, tracing their paths and revealing how matter flows between galaxies. The cosmic web structure is complex, and these whispers could act as tracers, showing how galaxies are linked across enormous distances by faint streams of intergalactic gas. Some whispers seem to weaken over time, hinting at how long they've been traveling through space. This decrease in signal strength might allow scientists to estimate their age and origin. If they can determine how long these whispers have been traveling, scientists could use them to trace events from different cosmic epochs. Each whisper's journey would then act as a record of the universe's changes over billions of years. The standard matter, or baryons, that have so far eluded cosmic astronomers may be located with the help of the intergalactic whispers. We are aware of its existence, but much of this stuff is diffused throughout intergalactic space, making it difficult to detect. If the murmurs point to regions with a high concentration of baryons, they could aid in the completion of the visible matter map. These baryons would be fundamental building blocks of the cosmos, illuminating the locations of galaxies and the invisible matter that links them. Intergalactic whispers, while faint and often overshadowed by brighter cosmic events, carry information that could help scientists understand the very fabric of the cosmos. Each whisper provides a clue to the vast hidden processes shaping intergalactic space, offering a glimpse into the forces at work in the spaces between galaxies. Through these subtle signals, the universe reveals itself piece by piece, and even the earliest ages of space and time. Extragalactic stars in void spaces. Extragalactic stars, drifting alone through the vast emptiness of space, offer a rare and intriguing look into the quiet, untouched regions of the universe. These stars don't belong to any galaxy. Instead, they float in cosmic voids, regions so empty that entire galaxies seem like faint dots in the distance. Stars like these are mysteries in themselves, silent travelers stripped from their galactic homes by forces unknown. left to wander the void in isolation. Often called nomad stars, these lonely stars have no nearby stellar neighbors and no galaxy to tether them, making them some of the most isolated objects in existence. Many of these stars were once part of galaxies, but got ejected due to powerful gravitational events. Imagine a galaxy merger where two galaxies collide and pass through each other, leaving chaos in their wake. In these clashes, stars can be flung out with incredible force, breaking free from the galaxy's pull. Some drifted out during these violent encounters, forced into isolation by the powerful tides of gravity, escaping only to end up in these quiet, almost lifeless cosmic voids. These spaces are so vast that they span millions of light years, so a single star within them is almost like a drop in the ocean, adrift and alone. There are cases where these extragalactic stars still cling to a companion. In the midst of all that emptiness, some stars manage to remain in binary systems, two stars orbiting each other, even without a galaxy nearby. These binary stars bring questions about what might have ejected them together and how they've managed to stay bound, even while floating far from other stellar masses. And there are rare examples where they're accompanied by a rogue planet, orbiting a single isolated star in the middle of nothing, creating a kind of solar system with no ties to any other structure. For any potential planets, this would be a unique environment, surrounded by the vast darkness of space with no other stars lighting up the sky. These lone stars aren't usually visible. They remain quiet and hidden from telescopes until they reach the end of their lives. When one goes supernova, it briefly lights up its surroundings, creating a stunning but lonely display. Without other stars around, the supernova event is a flash in the darkness, revealing a single isolated point of light before fading away. The remains of these explosions, neutron stars or black holes, are left in the void as silent reminders, remnants of stars that once burned brightly but had no galactic home. These explosions leave traces in the cosmic void, faint supernova remnants that may reveal themselves only to the most sensitive of telescopes, holding evidence of these stars' lonely existence. Some of these stars may even originate in galaxies' tidal tails, which is an intriguing possibility. When galaxies interact, they stretch each other out, creating long streams of stars and gas called tidal tails. Some of these stars escape entirely, flung off into intergalactic space where they drift on their own. These tidal events could be responsible for groups of extragalactic stars, remnants of once close connections that were broken by the gravitational tugs of nearby galaxies. So, even though these stars may seem isolated, their origins trace back to violent cosmic events, leaving a kind of faint fingerprint of their former galactic lives. Many extragalactic stars follow unique life paths, evolving in ways that may differ from their galaxy-bound counterparts. Without a galaxy's gravitational field, these stars drift farther and more freely than those anchored in clusters. Their life cycles might be subtly different, influenced by the lack of neighboring stars and the different environmental conditions in void spaces. Without the gravitational pulls and influences that typical stars experience, these isolated stars live their lives in near-complete solitude, experiencing a unique form of stellar evolution, unaffected by the complex structures within galaxies. These stars are essentially survivors. In cases of galactic cannibalism, where a larger galaxy consumes a smaller one, some stars manage to escape the chaotic merger. They drift off, escaping the galaxy collision's pull and entering void spaces as survivors, lone travelers from a devoured galaxy. What's left is a lonely remnant of that galactic history. A star set loose into the universe with no home, yet still carrying the memory of a past galaxy merger or interaction. Cosmic voids are some of the quietest, emptiest regions in the universe, stretching millions of light years across. For an extragalactic star, being in the middle of a void means existing in true isolation, with only a faint view of distant galaxies, scattered like tiny points of light across an otherwise dark sky. The distance between a lone star in a void and the nearest galaxy could be vast, making these void stars unique islands in an otherwise desolate sea. If any planets orbit these stars, they would experience a night sky unlike any other, a nearly pitch-black darkness with no Milky Way or bright clusters. just the dim glow of distant galaxies. We may learn more about the circumstances in these cosmic gaps from these stars as well. By studying their temperature, motion, and brightness, scientists can learn about the environment in voids, where density, temperature, distribution differ from galaxy-filled areas. Each of these stars is a small sample of how matter behaves in some of the universe's least populated spaces. The lonely paths of these stars might even hint at how dark energy affects objects in these regions, as dark energy drives the expansion of space at an accelerated rate. The lack of gravitational tethers allows extragalactic stars to move in unusual ways, often at high speeds. Some may have been launched by supernova explosions, sent speeding through space when their companion star exploded, freeing them from galactic gravity. These high-velocity stars add to the mystery, as their rapid motion could allow them to cover enormous distances over billions of years. Studying these star velocities can reveal insights into the powerful forces that set them in motion. A few extragalactic stars even travel with small clusters, hinting at a past where they might have been flung out together from a galaxy. These faint star clusters are rare, but their existence suggests that some stars were ejected in groups, possibly during tidal disruptions in galaxy mergers. They float together, disconnected from the main cosmic web of galaxies, forming a faint, distant reminder of a galaxy they can no longer call home. Detecting extragalactic stars in voids is a challenge. These stars are often so faint that only special techniques can reveal them. Gravitational microlensing is one such technique, where the light from a star briefly brightens as it passes near a massive object, like a distant galaxy or black hole acting as a lens. Microlensing allows astronomers to catch glimpses of these stars by magnifying their light, revealing them as they drift alone in the void. This technique is critical for detecting these stars, as traditional methods struggle to spot such faint, distant objects. Some isolated stars may even be near rogue black holes, ejected along with them from galaxies. These rare star-black hole pairings could be wandering the void, silently orbiting one another in the darkness. The presence of a rogue black hole near a lone star adds a new layer to the story, as these unusual pairs may be remnants of disrupted galaxies, bound together only by gravity in a quiet corner of the cosmos. The movement of these stars could also reveal how dark energy shapes the universe's structure. Dark energy, responsible for accelerating cosmic expansion, influences the motion of objects in low-density areas like voids. By observing the paths of these extragalactic stars, scientists might uncover hints of how dark energy affects stars without gravitational connections, a unique chance to study the force behind the universe's expansion. There's a small chance that some extragalactic stars host planets, creating planetary systems completely detached from any galaxy. For any such planets, life would evolve in an isolated system, experiencing extreme conditions with no nearby star systems. The darkness around them would be profound, with the sky showing only faint glows from distant galaxies. These planets would offer an incredible setting for studying the possibilities of life in the universe's loneliest corners, where conditions differ radically from those of planets within galaxies. Extragalactic stars don't just drift aimlessly. They act as tracers, reflecting the past interactions and movements of galaxies. They hold clues about galactic mergers, past collisions, and the dynamic forces within galaxy clusters. By studying them, scientists can map the motions of galaxies and uncover hidden aspects of cosmic evolution. Each star tells a story of its past, tracing its journey across vast stretches of space, connecting galaxies through the invisible ties of gravitational history. The fact that these stars are found in the middle of cosmic voids challenges what we know about the structure of the universe. They create holes, drift zones in the cosmic web, where visible matter is almost absent, showing that even the quietest regions of space may hold unseen history. Every extragalactic star is a reminder that the universe is full of mysteries, each a piece of the larger puzzle of how galaxies and the forces of the cosmos have interacted over billions of years. The topology of the universe. The universe's topology, the way space itself might be connected or shaped, opens doors to some of the most mind-bending possibilities in cosmology. Instead of focusing only on whether the universe is flat or curved, topology considers how space connects, how regions might loop or link in unexpected ways, and how these shapes could affect everything from the movement of galaxies to the behavior of light. The very space we live in may be more complex than it seems, with hidden twists, loops and paths that could change our view of the cosmos. Envision a cosmos where, if you go far enough in any one way, you may end yourself back where you began. One of the concepts of multi-connected topology is the possibility of space enclosing itself in a continuous loop. Even though there wouldn't be an edge in this universe, you could still travel the length of the galaxy and circle back to Earth. It would be like space folding in on itself, walking along a straight path on Earth and coming back to the same spot, despite the lack of an apparent edge or boundary, is analogous to this situation. The idea of a toroidal or donut-shaped universe is one of the most interesting ones in cosmic topology. The space-time continuum in a toroidal universe is infinitely curved, like a donut. According to this model, there is a finite quantity of space in the cosmos, but no physical limits or boundaries. Such a cosmos would eventually collapse rather than continue to grow indefinitely. Observations directed enough in one direction may, in theory, detect things emanating from a different side of the cosmos. Although it's an out-of-the-ordinary concept, it aligns with certain mathematical models that researchers use to analyze the structure of space. In a multi-connected universe, objects might even appear in multiple locations at once. For example, galaxies could have mirror images or ghost copies at different points in the sky. This duplication would happen because light could take different paths to reach us, showing the same galaxy from various angles. These mirror images would reveal themselves as repeated structures scattered across the universe, giving scientists a possible clue to the nature of cosmic topology. This kind of observation would be incredibly challenging to detect, but would provide direct evidence that the universe is connected in a unique and unexpected way. The concept of a crystallized or lattice-like universe takes the idea further, suggesting that space might have a repeating grid structure, with galaxy clusters arranged in regular patterns across vast distances. In such a model, the universe would resemble a cosmic crystal, with galaxies acting as points on a vast, three-dimensional grid. This pattern would be consistent across space, providing a level of order that suggests the universe is structured in a highly organized way. Observing a repeating structure on this scale would be difficult, but it would imply that the cosmos has a kind of hidden symmetry, like the atoms in a crystal. Cosmic voids, vast empty spaces between galaxy clusters, might also provide clues to the universe's topology. In certain topological models, the shape and size of these voids would reflect the overall structure of space, creating a pattern that repeats in specific ways. Voids could reveal the shape of the universe indirectly, as their distribution might follow the natural shape of the space they occupy. By studying voids and their locations, scientists may be able to map the underlying structure of the cosmos, using empty space as a guide to the universe's true shape. Some models propose that the universe's topology includes hidden dimensions. These extra dimensions are theorized to be curled up at tiny scales, making them impossible to detect directly. However, they would influence the way space connects, creating shortcuts or alternate paths across vast distances. In a universe with hidden dimensions, space itself could fold in ways we can't perceive, potentially allowing distant parts of the cosmos to be connected in ways that defy our usual understanding of distance. These extra dimensions wouldn't be visible to us, but would add complexity to the way space is structured, subtly affecting everything from galaxy movements to the paths of particles. Light in a multi-connected universe could take different routes to reach us. For instance, in a universe that wraps around on itself, light from a distant object might arrive at Earth by multiple paths, showing us the same object from different perspectives. This effect, known as path redundancy, would mean that light travels along different cosmic routes, revealing the same regions of space in different ways. Observing this phenomenon, could provide evidence that space loops or folds in unexpected ways, giving us multiple views of the same object in distant parts of the sky. If the universe is finite and has a specific topology, it could be edge-free yet limited. Similar to the surface of a sphere, which is finite yet has no edge, the universe could loop back on itself, creating a closed system with no boundary. This type of structure would mean that even though space is limited in size, it would have no true end or boundary. You could travel infinitely without ever reaching an edge, as space would fold back on itself, maintaining continuity without requiring an actual boundary. Theoretical shapes beyond the typical 3D perspective challenge our intuition. Ideas like the Klein bottle or projective plane introduce non-intuitive shape where movement behaves differently from typical 3D space. These shapes are challenging to visualize, but would allow for unique travel paths and connections across the cosmos. If the universe followed one of these unusual topologies, it could allow paths through space that create unexpected connections, giving rise to entirely new perspectives on distance and location. Imagine a universe with a Moebius strip structure. Movement along a Moebius path would flip perspectives, allowing travelers to see objects from new angles after making a full circuit. In a cosmic version of a Moebius strip, light and matter could interact in unusual ways, bending and twisting as they loop through space. Such a topology would change how we perceive the universe's layout, as movement in one direction might reveal hidden angles and views of known objects. If the universe's topology includes closed loops, there could be paths through space-time where time itself reconnects, creating closed, time-like curves. In theory, these curves could allow objects to follow a path that eventually brings them back to their original time and location. While highly speculative, these time loops suggest a topology that links time and space in a way that allows for circular movement not only through space, but through time itself. Such a structure would hint at deep connections between space, time, and the fundamental nature of the universe. In a multi-connected universe, it's possible that we might even see echoes of our own galaxy in the distance. If space folds in on itself, our galaxy could appear as a distant object from different perspectives, creating ghostly copies that show our own Milky Way in another part of the sky. These galactic echoes would be faint and difficult to detect, but would provide fascinating evidence of a looped or folded universe. Finding an image of our own galaxy far across space would be a groundbreaking discovery, proving that the universe connects in ways beyond our usual three-dimensional understanding. The shape of the universe may even impact the way gravity behaves on large scales. In a finite but unbounded universe, gravity might follow different rules, influencing galaxy formation and the structure of space itself. A multi-connected or lattice-shaped universe could lead to gravitational effects that reinforce certain patterns in galaxy clusters, enhancing certain structures, and potentially altering the way galaxies move over time. Gravity's behavior on these scales could reveal clues about the true shape of space, as it interacts with matter in ways that reflect the cosmic topology. If extra dimensions exist, they might allow for shortcuts across space, connecting points that seem far apart in 3D space. These shortcuts, theoretically created by hidden dimensions, would make it possible for objects or light to travel between distant regions of space faster than through normal space. Such connections could allow galaxies that seem separated by vast distances to interact in subtle ways, influenced by the hidden geometry of extra dimensions. These shortcuts would change how we think about distance, potentially creating a universe where separate regions are more connected than they appear. The universe's topology could also test fundamental symmetries in physics. Certain topologies would only be possible if specific symmetries, like reflection or rotation, hold on a cosmic scale. By studying these shapes, scientists can explore the laws of physics themselves, looking for patterns that align with different topologies. If the universe has a specific shape, it might confirm that certain symmetries are universal, shaping the structure of everything from particles to galaxies. This connection between topology and symmetry could reveal insights into the foundational principles that define our universe. The idea of a multi-connected, looping, or lattice-like universe reveals that the true shape of space might be more intricate than we realize, with hidden connections and paths that define the structure of everything we see. From cosmic shortcuts to mirror images of galaxies, the universe's topology holds answers to some of the deepest mysteries in cosmology. Exoplanet, atmospheres and biosignatures. Exoplanet atmospheres may hold some of the most promising clues in the search for life beyond Earth. By studying these distant worlds, scientists look for specific chemical fingerprints, known as biosignatures, that could signal the presence of life. Different atmospheres present different opportunities, and the variety of potential indicators creates a rich and complex search field, stretching our understanding of what life might look like under alien skies. Certain chemical combinations are particularly striking. For example, finding both methane and oxygen in the same atmosphere would be highly unusual without biological processes. On Earth, these two gases are kept in balance by living organisms. Methane comes from microbes and other life forms, while oxygen is produced by plants and photosynthetic organisms. Left alone, these gases would react and cancel each other out, so their simultaneous presence in an exoplanet's atmosphere could be a hint that something, perhaps life, is actively maintaining this balance. Exoplanet vegetation, if it exists, might create unique color signatures in the light reflected off the planet's surface. Photosynthetic pigments on Earth produce a strong green signature due to chlorophyll, but alien plants or photosynthetic organisms might have different pigments suited to their star's light. For instance, plants under a red dwarf star might develop dark red, black, or even metallic pigments to absorb more light. These color variations could give away the presence of photosynthesis on distant worlds, allowing scientists to spot colors that don't match simple mineral surfaces. Volcanic activity on exoplanets could also provide indirect hints of life. Volcanoes release gases like hydrogen, sulfur, and methane, which certain microbes can use for energy. If a planet has both volcanic activity and signs of life-compatible gases, it might suggest an ecosystem fueled by volcanic emissions. In such environments, organisms could survive by using volcanic gases as a chemical energy source, similar to life forms that live around hydrothermal vents on Earth. Some exoplanets may even show changes in atmospheric composition as seasons shift. Just like on Earth, where plant growth changes with the seasons, extraterrestrial biological processes might cause seasonal fluctuations in the levels of certain gases. For instance, the rise and fall of a gas like oxygen or methane during specific seasons would hint at biological processes tied to seasonal cycles. Seasonal biosignature changes could reveal a living ecosystem adapting to its planet's climate, cycling with natural rhythms that impact life on a larger scale. In some cases, hazy atmospheres full of hydrocarbons or organics might indicate biological activity. On Earth, certain microbes produce hazes as byproducts of their metabolism, creating atmospheric hazes filled with organic particles. If a planet's atmosphere has thick, organic-rich hazes, it might be a sign that life is actively producing these particles. These hazes could reflect the presence of microbial communities thriving in the upper layers of the atmosphere, suspended in a hazy environment created by their own metabolic activity. Advanced civilizations, if they exist, might also leave signatures of their presence in exoplanet atmospheres. One possible technosignature could be unusual metal vapors or industrial byproducts that don't naturally occur in planetary atmospheres. For instance, compounds associated with metal processing or synthetic chemicals could point to technological activity. An atmosphere with high levels of rare metals or artificial compounds might hint at industrial processes, revealing the possibility of a civilization actively shaping its environment. Certain stars emit powerful flares that can impact the atmospheres of orbiting planets. On planets orbiting volatile stars, biosignature gases could face regular disruption by stellar flares. Studying how these gases react to flare activity can reveal their resilience to harsh conditions and hint at life's adaptability in environments exposed to constant radiation. If biosignature gases consistently reappear after flares, it could suggest a stable, biologically maintained atmosphere, resilient to stellar activity. Nitrous oxide is another potential biosignature that's often overlooked. This gas is produced by microbes and plays a significant role in Earth's nitrogen cycle, yet it rarely appears in discussions of biosignatures. Detecting nitrous oxide in an exoplanet's atmosphere could suggest microbial processes, adding an alternative signature to the more common markers like oxygen and methane. Finding nitrous oxide could imply the presence of microbial life in places where other forms of biosignatures might be sparse or missing. The stability of an exoplanet's atmosphere itself might be a clue. A stable atmosphere indicates equilibrium, whereas an unstable atmosphere with rapidly changing chemical layers might suggest ongoing biological or geological activity. An atmosphere in flux could be a sign that processes, whether biological or geological, are actively altering its composition. Detecting such instability would suggest that the planet's atmosphere is more than just a passive layer, and that something might be driving its constant change. Some planets may have hydrogen-rich atmospheres, which would make them very different from Earth. Certain microbes can survive and even thrive in hydrogen-dense environments, meaning these atmospheres might support forms of life unlike anything we see on Earth. If biosignature gases are found in a hydrogen-rich atmosphere, it could suggest life that relies on hydrogen rather than oxygen, adding to the diversity of possible life-supporting environments beyond Earth-like conditions. On a planet with an intelligent civilization, artificial lights could create unusual nighttime reflections. In cities, for example, artificial lights would produce light pollution, and on a distant exoplanet, this could appear as a glow on the planet's night side. If we detect such artificial illumination, it could reveal the presence of technologically advanced life. These city lights would be a clear technosignature, offering a rare glimpse into artificial structures on distant worlds. The discovery of rare element ratios could also point to industrial processes. Some isotopes, like certain forms of xenon or technetium, are uncommon in natural settings, but can be produced by nuclear reactions or artificial processes. Detecting unusual levels of these elements could suggest technological activity or artificial manipulation of the atmosphere. These artificial isotopes would act as markers of industrial processes, hinting at a civilization's ability to manipulate its environment. On a molecular level, water clouds in unexpected places could reveal habitable microenvironments within otherwise inhospitable atmospheres. Some exoplanets might have liquid water clouds at high altitudes, creating pockets where life could exist in the upper atmosphere. These water-rich zones would be isolated from harsher conditions below, providing unique islands of habitability. Detecting water clouds at specific altitudes might reveal regions where life-supporting conditions are present, even if the planet's surface remains uninhabitable. Certain complex molecules in exoplanet atmospheres may imply the presence of enzymes. On Earth, enzymes are essential for complex biochemical reactions, allowing organisms to build and break down molecules efficiently. If specific byproducts associated with enzymes appear in an exoplanet's atmosphere, it could indicate biochemical processes. This would hint at complex life forms capable of using enzyme-like activity to alter their environment, providing a powerful biosignature that goes beyond simple gas markers. Some planets experience unique weather phenomena, like silicate rain, where silicate compounds condense and rain down due to extreme temperatures and pressures. This exotic rain would indicate complex atmospheric chemistry, possibly supporting life forms adapted to mineral-rich environments. Silicate rain would create conditions far different from those on Earth, yet it might allow for unique ecosystems that thrive on minerals rather than organic compounds. The presence of carbon-phosphorus compounds could also be an indicator of life-supporting conditions. Phosphorus is rare in space, but crucial for DNA and other biological molecules. Detecting carbon-phosphorus compounds in an exoplanet's atmosphere would suggest that life-friendly chemistry is taking place, as phosphorus availability is often a limiting factor for life. The discovery of these compounds could reveal conditions that support biochemical processes similar to those on Earth. A self-sustaining chemical cycle could point to biological processes. If a planet's atmosphere shows a cycle where compounds continuously regenerate without external influences, it might imply life's presence or even primitive self-replicating systems. These cycles would reveal a level of chemical stability that could only occur with active processes keeping the cycle intact, suggesting that life, or something lifelike, is at work maintaining these patterns. Exoplanets with thick, organic-rich hazes might resemble Earth's early atmosphere before life fully took hold. These hazes, filled with complex hydrocarbons, would create conditions for prebiotic chemistry, the chemistry needed to produce life's building blocks. In these hazy layers, molecules could form and interact in ways that set the stage for life. Observing organic hazes on exoplanets could reveal planets where life is just beginning to emerge, potentially allowing us to witness early stages of biological development. Barion acoustic oscillations, BAOs. Barion acoustic oscillations, BAOs, are like ancient sound waves, echoes from the earliest days of the universe. They began as pressure waves traveling through the hot plasma that filled the young cosmos, driven by interactions between photons, particles of light, and baryons, particles like protons and neutrons. These waves created ripples in the matter, forming patterns that still shape the way galaxies are distributed today. Frozen in the cosmic web, BAOs left a lasting imprint on the universe, creating a repeating pattern in the large-scale structure of matter that scientists use as a kind of cosmic ruler. At a time before stars, galaxies, or even atoms, the universe was a hot, dense soup of particles and radiation. Within the first 380,000 years, gravity pulled matter together, while the intense pressure of radiation pushed it outward. This balance between gravity and radiation created oscillations, ripples, moving through the plasma like sound waves. But as the universe expanded and cooled, these oscillations froze into place, leaving an imprint that can still be seen in the clustering of galaxies billions of years later. Important roles BAOs play is in helping scientists understand the rate of cosmic expansion. Since these oscillations left a characteristic scale of roughly 500 million light-years, they provide a standard ruler that researchers use to measure vast cosmic distances. By observing the BAO pattern at different points in the universe, scientists can track changes in the rate of expansion over time. This standard ruler is essential for measuring how dark energy affects the universe, offering insights into the force driving its acceleration. BAOs are visible in the cosmic microwave background, CMB, the afterglow of the Big Bang, where they show up as subtle temperature variations. These temperature differences reflect the pressure waves in the early plasma, marking regions of high and low density. From these high and low pressure zones, BAOs left their imprint, an echo of the universe's early structure preserved in the CMB. This connection between BAOs and the CMB gives scientists a snapshot of conditions when the universe was just a few 100,000 years old. Gravity played a crucial role in shaping these oscillations. As the universe expanded, gravity acted like an anchor, holding the oscillations in place once the plasma cooled and the photons escaped. With gravity's help, the BAOs became permanent features of the cosmic landscape, guiding the formation of galaxies and clusters that followed. Today, the BAO signal remains embedded in the distribution of galaxies, showing a preferred clustering distance around 500 million light-years. This pattern is like a cosmic fingerprint, identifying BAOs as the markers of early cosmic structure. To map BAOs, scientists use galaxy redshift surveys, which measure the distance of galaxies based on how their light stretches as the universe expands. Projects like the Sloan Digital Sky Survey, SDSS, have mapped millions of galaxies, revealing the faint but distinct pattern of BAOs across vast distances. By measuring these clustering patterns, scientists gain a clearer picture of how galaxies are spread out, following the ancient BAO scale set billions of years ago. The repeated clustering of galaxies isn't random. It's a relic from the early sound waves that rippled through the young universe. These oscillations didn't just influence galaxies, they affected intergalactic hydrogen gas as well. By studying the gas between galaxies, scientists observed the BAO pattern in a different form. Quasars, distant objects that shine brightly as matter falls into supermassive black holes, help reveal this structure. The light from quasars passes through hydrogen gas clouds on its way to Earth, and as it does, it encounters the BAO pattern. By analyzing the absorption of light in these clouds, researchers can detect the BAO scale, even in the intergalactic medium. BAOs also provide essential information about the geometry of the universe. If the universe were curved, the distances measured by BAOs would change over time. but measurements of BAOs across billions of years suggest that the universe is flat on large scales, confirming a key feature of cosmic geometry. This flatness fits with predictions from inflation, the theory that the universe experienced a rapid expansion shortly after the Big Bang. BAO measurements support this idea, helping confirm that inflation left the universe flat as it expanded. The characteristic BAO scale of 500 million light-years is stable across cosmic time, meaning that as we look at different epochs, we see the same pattern repeated. This stability makes BAOs a reliable cosmic ruler, and by measuring this scale at different redshifts or distances, scientists can study how the expansion of the universe has changed. These measurements are crucial for understanding dark energy, as they show how this mysterious force has influenced the universe's growth rate over billions of years. BAOs are also important for understanding the distribution of dark matter. Dark matter doesn't emit light, but it interacts with gravity, creating regions of high density where matter gathers. These regions align with the BAO pattern, as dark matter anchors the oscillations, holding them in place. The clustering of galaxies and dark matter follows this pattern, so studying BAOs helps scientists map the dark matter structure of the universe, even though dark matter itself remains invisible. In addition to galaxies and gas, BAO patterns can be observed in cosmic voids, the large empty spaces between galaxy clusters. Just as galaxies cluster around the BAO scale, voids show a complementary pattern, revealing areas where matter is absent. These voids highlight the cosmic web structure, with dense clusters of galaxies separated by vast empty regions. By studying both the galaxies and the voids, scientists get a complete picture of how BAOs shape the cosmic landscape. Unlike gravitational waves, which are ripples in spacetime caused by massive events, BAOs are density waves. They represent regions of matter concentration rather than distortions in the fabric of space. This distinction is important, as it shows that BAOs don't alter the path of light directly. Instead, they create patterns in the distribution of matter, making them a different type of cosmic ripple compared to gravitational waves. The fact that BAOs may be observed at various redshifts gives them further intrigue, as it allows researchers to study them throughout the universe's history. From the Big Bang to the present day, physicists may trace the expansion of the universe by monitoring BAOs at different redshifts. To better comprehend the development of large-scale structures, dark energy, and cosmological theories, this tracking is crucial. Some of the most detailed studies of BAOs come from examining the Lyman alpha forest, a series of absorption lines in the spectra of distant galaxies and quasars. These lines are created as light passes through hydrogen clouds, which absorb specific wavelengths. The Lyman alpha forest reveals the distribution of hydrogen gas, allowing scientists to detect the BAO scale even in regions far from galaxies. This pattern in the hydrogen gas clouds reflects the same structure seen in galaxies, showing that BAOs influenced not just galaxies, but also the vast reservoirs of intergalactic gas. BAOs even play a role in studying neutrino masses. Massive neutrinos, tiny particles that interact weakly with other matter, affect the formation of large-scale structures. By analyzing how BAOs are distributed, scientists gain clues about neutrino masses, which are otherwise difficult to measure. The impact of neutrinos on BAO structure helps scientists refine their understanding of these elusive particles and their role in shaping cosmic evolution. BAOs have also offered evidence for a flat universe. If the universe were curved, the BAO distances would vary depending on the scale and angle of observation. But by analyzing BAO measurements across different parts of the sky, scientists confirm that the universe is flat on large scales, supporting one of the key predictions of the Big Bang model. This consistency reinforces the idea that the universe's geometry is a direct result of the inflationary period, which set the initial conditions for cosmic growth. Through BAOs, scientists can test models of dark energy. Different models predict different expansion rates for the universe, so by measuring BAO patterns across time, researchers can distinguish between these theories. BAO data has become essential for testing dark energy models, as it provides a precise and reliable way to measure cosmic acceleration. These measurements suggest that dark energy's influence has been consistent, adding to our understanding of how it shapes the universe. The persistence of BAO patterns offers a view of the pre-galactic universe, capturing a snapshot of cosmic structure before galaxies formed. These oscillations formed when the universe was filled with plasma, long before stars or galaxies existed. By studying BAOs, scientists gain insights into the universe's earliest conditions, exploring a time when matter was just beginning to organize itself into the structures that would eventually form galaxies and clusters. BAOs stand out as a cosmic ruler, a tool for measuring distances across billions of years. From the early pressure waves that shaped matter distribution to the persistent patterns we see today, BAOs link the universe's early days to its present structure. These oscillations are not only relics of the past, but also active guides in our study of the universe, revealing how matter has organized. Through BAOs, the mysteries of the universe become just a bit clearer, showing how sound waves from the dawn of time continue to ripple through space, marking the rhythm of cosmic evolution. The Lyman Alpha Forest. The Lyman Alpha Forest is a series of absorption lines observed in the light from distant quasars, each line marking a patch of hydrogen gas that the quasar's light passed through on its journey to us. Quasars, which are incredibly luminous objects powered by supermassive black holes at the centers of distant galaxies, act like cosmic flashlights, illuminating clouds of hydrogen gas that lie in between. These absorption lines appear as narrow dips in the quasar's spectrum, creating a forest of lines that scientists call the Lyman Alpha Forest. Each absorption line in this forest is like a shadow left by a hydrogen cloud, a region in space dense enough to absorb specific wavelengths of light. When we observe these shadows, we're seeing evidence of hydrogen that has traveled billions of years to reach us. The beauty of this phenomenon lies in how it reveals not just one cloud of gas, but a whole series of them, stretching across vast distances in space. Each of these clouds represents a different time and place, a snapshot of how hydrogen was distributed across the universe in the past. This forest isn't just a pretty pattern, it's a cosmic timeline. The further away a quasar is, the longer its light has traveled to reach us. So, the Lyman Alpha lines from distant quasars show hydrogen clouds as they existed billions of years ago. Observing these lines lets scientists trace the evolution of hydrogen over cosmic time, revealing how it clumped together, how it spread out, and how it changed as the universe aged. Each line in the forest tells the story of the universe's past, showing how it looked in different eras. The Lyman Alpha Forest provides information on the temperature of the hydrogen clouds it maps, which is an intriguing feature. Scientists can roughly determine the cloud temperatures by analyzing the breadth of the absorption lines. The gas is considered colder when the lines are narrow and warmer when the lines are wide. Using these widths as a gauge, astronomers may trace the temperature history of the cosmos, from its primordial blazing hot days to the current, cooler but no less active state. Each hydrogen cloud, with its own spectral line, is analogous to a thermometer that displays the cooling of the cosmos over billions of years. Another important period in the history of the cosmos that the Lyman Alpha Forest sheds light on is the reionization epoch. Neutral hydrogen was formed when charged particles in the expanding and cooling cosmos that followed the Big Bang fused together. A dark age, without stars or galaxies, was ushered in by this event in cosmic history. Hydrogen was reionized and broken down into charged particles by the energy of the earliest stars and galaxies when they finally formed. The Lyman Alpha Forest records this change, showing how neutral hydrogen patches were ionized over time as starlight illuminated the cosmos. Each line in the Lyman Alpha Forest also shows how cosmic expansion affects these hydrogen clouds. As the universe expands, light from distant objects gets redshifted, stretching to longer wavelengths. Each absorption line shifts slightly, depending on how far away its hydrogen cloud is, letting scientists measure the universe's expansion at different times. By observing these redshifts in the Lyman Alpha Forest, astronomers can study the universe's growth rate, using the forest as a cosmic ruler to measure distances and see how fast space has expanded across different epochs. Variations in the Lyman alpha forest might reveal the presence of exotic particles. If particles like dark photons exist, they could interact with hydrogen clouds in unusual ways, creating unexpected shifts or patterns in the forest of absorption lines. Though it's a speculative idea, any unusual or unexplained features in the forest could hint at particles we've never observed before, hidden in the faint shadows of hydrogen. The Lyman alpha forest is also a way to detect the influence of early black holes. Black holes exert powerful gravitational forces, pulling in surrounding gas and heating it up. This heated gas can affect nearby hydrogen clouds, causing subtle shifts in the Lyman alpha lines. By identifying these shifts, scientists can find clues about black hole formation in the early universe, revealing the role black holes played in heating the surrounding gas and shaping the conditions of the cosmic landscape. In this way, the forest serves as a record of both black hole growth and its impact on the surrounding hydrogen. Even after reionization, not all hydrogen became fully ionized. Pockets of neutral hydrogen remained scattered throughout the universe, and the Lyman alpha forest reveals these lingering patches. These areas of neutral gas help scientists understand the limits of reionization and how starlight spread unevenly across the universe. In a sense, these pockets act like cosmic time capsules, preserving a glimpse of the universe's early conditions long after most hydrogen became ionized. Powerful galactic winds generated by star formation can also influence hydrogen clouds. When galaxies form stars at high rates, they produce intense winds that push gas outward, impacting nearby hydrogen clouds. These winds can shift the positions of Lyman alpha lines, providing clues about the feedback processes between galaxies and their environments. This interaction between galaxies and hydrogen gas helps scientists understand how galaxies and their surroundings evolve together, with the Lyman alpha forest capturing the effects of these interactions over time. A natural instrument for calibrating cosmic distance measurements is the Lyman alpha forest. A consistent set of markers may be used to cross-check and refine distance estimations, since the forest occurs in the spectra of quasars over large distances. In order to verify the accuracy of our universe maps, this is especially helpful for comparing various approaches to estimating cosmic distances. The forest's regular layout makes it a useful cosmic yardstick for gauging the actual size of the cosmos. The early universe had weak magnetic fields that could still influence the behavior of hydrogen clouds. If these primordial magnetic fields did exist, they might have slightly affected how hydrogen clouds were arranged, causing slight distortions in the Lyman alpha forest patterns. By studying any unusual shifts in these patterns, scientists could find indirect evidence of these ancient magnetic fields, providing clues about the physical conditions in the universe's earliest days. Galaxy clusters, the largest gravitationally bound structures in the universe, can also affect nearby hydrogen clouds. These clusters create gravitational effects that slightly shift the Lyman alpha forest lines, offering indirect evidence of where galaxy clusters are located. Although the clusters themselves don't appear in the quasar spectrum, their influence leaves a mark on the surrounding hydrogen, helping scientists map these massive structures across the universe. Some of the absorption lines in the Lyman alpha forest reveal traces of metals, elements heavier than hydrogen. These metals likely originated from supernova explosions of early stars, which spread heavy elements into surrounding hydrogen clouds. Finding traces of metals in the forest shows that the first generation of stars had already exploded, enriching their surroundings with new elements. This discovery provides a snapshot of chemical evolution, showing how early stars changed the composition of the universe by introducing the elements needed for future star and planet formation. The temperature history of the intergalactic medium, essentially the space between galaxies, is preserved in the Lyman alpha forest. By tracking changes in line widths and positions, scientists can reconstruct how this medium heated and cooled over time. Different sources of energy, like starlight, black holes, and even cosmic winds, have all influenced the temperature of the intergalactic medium. The forest offers a continuous record of these temperature changes, showing how energy from stars and galaxies impacted the vast stretches of space between them. Each of these features makes the Lyman alpha forest an invaluable tool for studying the universe's history and evolution, From tracing cosmic temperatures and mapping early black hole activity to hinting at exotic particles and ancient magnetic fields, this forest of hydrogen shadows offers a unique, detailed view into the events that have shaped the cosmos. In exploring the mysteries of the universe, we journey through concepts that defy our intuition and stretch our understanding. I hope you enjoyed this video. If you did, feel free to subscribe to the channel. Thanks for watching.